হ্যাঁ, শুনতে পেলাম রেকর্ডিং ইন প্রগ্রেস।
Okay. Okay, so welcome everyone to this week's colloquium at the School of Astrophysics. We are glad to have Dr. Sunit Mukherjee from University of Massachusetts Lowell as our speaker today. Like many of our speakers in this colloquium series, Sunit is an alumnus of the Physics Department of Presidency University. Sunit did his BSc from 2012 to 2015. And after that, a unique thing happened. At that time, we started a MOU with UMass Lowell, and we had plans for some exchange students and programs. And as part of that, Sunip actually joined UMass Lowell as a PhD student. Usually in American universities, students join after 4 years of undergraduate studies. Sunip had 3. So there had to be some special discussions and arrangements. And since Sunip was very interested to do instrumentation related stuff, and there were a lot of opportunities there, so that was one of the reasons why he was admitted. And after doing some additional coursework there, he joined the PhD program, and then he did his work on the thesis, which he will talk about a little bit, partly.
Not at all.
mentioned in passing. And then after finishing his PhD, as most instrumentalists do, he continued to work in the same lab as a postdoc. Because once you work in a lab as an instrumentalist for 5 years, then the lab cannot let you leave. That's one of the things. So now he's a postdoc in that lab, and he will talk about some of his work. We have heard of some of Sunit's work from Professor Supriya Chakraborty, who is the advisor of Sunit's thesis last year, when we did the opening of the new computer, upgraded computer lab. I think I'll just, well, I mean, I can give a whole talk on Sunit, but I can do that. I think there is the estimate. Everyone can give a separate whole talk on Sunit, but we so can't do that. Sunit colloquium. That is his version. It's his version. But Sunit was this proverbial sort of. His mom will wake up at night hearing some noises and discovered that Sunit just opened the entire television set up and trying to fiddle with various instruments inside the television set and so on. So he had this knack of fiddling with instruments, but he also had the knack of fiddling with equations and computation, etc. For a long time, many of us used to go to Sunit to ask about any problems regarding computation. Sunit has done some work with some of us, generating some simulation and so on. So Sunit had sort of interest in all of these things, but I think instrumentation was one of the things that he liked most, and it's great that he has continued to work on that. And I should also mention that Sunit also faced challenges regarding, I'm particularly mentioning this because there are students here who have similar challenges in sort of finishing up things. Like Sunit would start many different things, but may not finish all of them. It will take time to wrap up things. Maybe because he was too much of a perfectionist and he didn't want to finish before something is perfect and so on. But sometimes done is better than perfect, and we need to understand. So I'm very glad to see that Sunit actually, continued to do this work, and after finishing PhD is continuing his work as a postdoc fellow. And so we'll hope to see other instruments that fly in space, which are made by Sunit. So without further delay, I have this one anecdote. I mean, it's not the Sunit Talk series, but our current registrar, this is another aspect of Sunit, that our current registrar, who used to be the controller of examinations when the university started, I was telling,
Shunib going to Lowell and all that. Oh, Shunib. Oh, the physics Shunib. Yes. How do you know him? The default as Shunib. The challenges that you are talking. How are you going to default? Always late on
late on
Paperwork.
yes, late on filling up the form for exams and all these things.
But
so the point is that I mean Shunib had to change these things to become what he has become today. It's not like he continued to do that and still because he had to ultimately finish up stuff.
Are you lost some past mistakes?
So yeah. So I guess that's probably not what you mean, but that's
No, that's exactly what I mean.
okay. So and we also have guests from I think one from who just finished masters at the University of Arizona in optoelectronics, optical engineering, and from Kolani Engineering College, electrical. So okay, so this is not the usual introduction that we give. I mean, we give a more formal one, but.
And this will also be a very informal talk. I will be honest, I'm on vacation. I was in vacation mood until like 12 p.m. today. So this will be a fairly informal talk, and I'll come clean. A lot of this talk is actually sort of cleaned up from the previous talk I did back during COVID time, September the 30th.
Okay, so please start.
Yes. So I'll actually talk about a bit of that project, the mistakes that we made, we as a group, and what I guess we learned as a group from those mistakes. So that's why a physics-trained software person's guide to making a CubeSat, because I am a physics person. I was trained in physics here in this very building, but I guess I had a bit of a calling doing software. So as professors and my friends, one of them was sitting there in the back, he'll attest to, excuse me, I like to do software. And if you do software, if you write code to tackle problems, you learn certain things. And I guess I'll try to sort of convey that knowledge, or more like how I learned doing different things. That's sort of the point of the talk. So that's why this very sort of Kubrick-esque title, A Physics-Trained Software Person's Guide to Making a CubeSat, or How You Learn from Your Past Mistakes. So I guess I'll open with what a CubeSat is. A CubeSat is a small satellite. It's the name cube implies it's made of little cubes. The cubes are usually 10 centimeter cubes, so it's 10 centimeter on all sides. And usually each this 10 centimeter cube thing is usually about a kilogram, 1.33 kilogram if you go by the standard. They usually come in this 1U, 2U, 3U. So 1U is this one little cube. You put a second one on, that's a 2U. Put a third one on, that's a 3U. And then you can put two of them side by side, that's a 6U. And you put two of these 6Us on top of each other, you got a 12U. So there are all of these different sizes. They're usually cheaper to fly because when you're flying a normal satellite, they have a bunch of like excess capacity left, but usually satellites are a certain shape, so it's hard to fit another large thing with it. So if you make these small items, they can sort of do a ride share and take you up with other things. And since these are small, these are also cheaper to build. Because less material, you're probably not really worried about these actually staying up in space for long. So you can make them with consumer components that are also inexpensive. And the good thing about these things is, since they're small, what you can do is you can put many of these up in space, and you can do things that are hard to do otherwise. For example, if you want to do global coverage of Earth itself. If you just have one satellite looking at a part of the land, and then it's just, the Earth is rotating, it is in orbit, and that way you want to cover the entire globe, it's going to take you some time. But imagine if you have 100 of these small things in different orbital orientations, you can probably cover the entirety of the Earth in about 20 minutes time. So you basically have a global map that's updating every 20 minutes. And that's great. So that picture, top right, that's a satellite called Dove. That does exactly that. It's a swarm of 100 plus satellites that builds a RGB map of the Earth roughly about 20 minutes, every 20 minutes. And if we look at the main barrier to entry to space, it's usually launch price. So it's cost per pound of payload on the y-axis and payload to that orbit, how much it costs. And you can see that the cost really goes up as the back in the day the costs were high. Now the costs are coming down, but they're still fairly high, so that a small university or a small student group cannot afford it. So this is an old statistics of CubeSat launches that I showed back in my talk in 2020. And you can see that 2017 saw about 300 CubeSat launches, and 2018, this paper was actually written in 2019, so they didn't have the complete data of 2018. But if I look at what's up now, you'll see that we have been regularly launching 300 plus CubeSats every year. So that means that even the industry has found interesting applications of CubeSats and small sats. So that's why we're seeing such high number of launches. And this doesn't even include your Starlinks and so on, because if you add that to this list, this number is going to inflate even further. Now, I have been talking about CubeSats and satellites, but what is a satellite? So can someone here tell me what a satellite is? Anyone? I need a volunteer. Sure, orbit. What else? What is a satellite? What does it do?
Some other mass around which it is.
Right.
Its mass has to be less than.
Right. But that's the physics definition of a satellite. A rock can be a satellite, but in the context of this talk, like when we say, right, right. So this is what I call the dumb breakdown of a satellite. So a satellite has two parts, one part that does something, the other part that helps the actual doing something part. And the do something part is the scientific payload, because some payloads are not scientific. If you have like a radio broadcast relay or something, like the thing that you watch your television on, that's not a scientific payload, but it's a payload nonetheless. And then to help the payload do something, you have all of these other parts. So for example, you have a mechanical body, a structure that holds everything in place. If you want to change its shape for some reason, for example, you have solar panels that you want to open up to increase your surface area. So it's a change of shape, but it has to be done in a controlled manner. That's very important, with intention. Then you have to have a part that powers everything on your satellite. Then you have to make sure that your satellite doesn't spin like crazy, or you have to point at something interesting. If you're imaging the Earth, you need to point at the Earth. If you're imaging some star, and for example, you're doing a Hubble deep field, you want to look at the same patch of the sky for days on end without moving. So you need to be able to do that. And then once you take your nice deep field picture, you need to beam it down to Earth, or you need to tell your Hubble, okay, now point there and take your deep field. So that kind of stuff. So you have some data telemetry and commanding. And then you have to also make sure that the science, the payload, doesn't go crazy. That's also part of this help to do something. So that's sort of the common people lingo of what a satellite is, sort of broken down. And these are the more sort of official names of those exact things. So a satellite is broken in two parts. One is the mission system, that's your payload, that can be scientific or a technological payload. And then you have the bus systems, where you can sort of equate the body of the satellite as the bus and the payload as the passenger. And so the bus system is comprised of these different parts where you determine your attitude, where you're pointed, and you actually control where you're pointed. You have to have communications to get data on and off. You have a power supply. You have command data handling to interact with your payload. And you have a structure that sort of encloses this whole thing in. So that's the basic of a satellite. Now I'm going to switch gears, and now that we have sort of idea of what a satellite is, what the different parts of it are, I'm going to talk about the previous satellite that I did, and I talked about this in 2020. This has actually, when I talked about it in 2020, it was still kind of being made, but since then it has actually flown. I can show you guys some pictures after the talk if you want. So let's talk about that. It's called Spacehawk. It kind of looks like that. It's empty at that point the picture was taken. This is only the structure part of it. It's a 3U CubeSat, so each of these is like a U. And what is Spacehawk? It is the science program around communication engineering with high-achieving undergraduate cadres. This is my advisor's acronym. He is great at doing acronyms, and I honestly am very bad at it. So we'll move on from this as fast as we can. So this is sort of the side view of Spacehawk as a CAD model. And this is the exploded view of it. And I want to go over this for a minute because this will basically describe, this will contextualize Spacehawk in terms of that initial sort of flow diagram that I showed, like a breakdown of what a satellite is. So, oh, awesome, thank you. That's fine. So these are the solar panels. That's the part of the structure. Then you have all of these things on the sides that are also parts of the structure. And then we have inside, we have these different boards. These different boards are actually performing the different bus functions of the satellite itself. So this one, for example, this is actually the power system. It houses the battery. It takes power from all the solar panels, and it powers the rest of the system. This board in here, this was actually made by us. This is the attitude determination and control system. And this has a couple of magnetic torque coils. We'll get to that later. Then this is the communication radio. That's the sort of the secondary communication radio that we bought from a company. And this is what was used for commanding the system. And everything down here, all of this was our payload. The payload comprised of a computer and this board, which is basically a phased array system, which drives 16 antennas in unison so that you can form a beam and you can steer like a radio beam. You can steer it without actually moving your spacecraft, which is very important because if you want to send down a lot of data, you need to have, you need to be able to basically track, because you're moving in the sky, you're moving at about 8 kilometers per second. So if you want to maintain a long link, then you'll have to have a way of basically looking straight at the antenna that you're sending your data down to. But you're moving, so you have to move your satellite to do that. But moving a satellite is slow. So that's where, if you do all of this electronically with 16 antennas, that helps. So in the context of a satellite, all of this is our payload. We have the different bus boards. We have a structure. We have a power system, attitude control, communications, all of that. So that's great. And what did Spacehawk intend to do? Again, so it was a 3U CubeSat, and the goal was first to train undergrads so that they could actually work on a satellite project. And then we wanted to demonstrate a student-developed high-data X-band communication system from ISS-like orbit, which is 400 kilometers altitude and 51.6 degree inclination. And we had a bunch of operation goals. So when you have a satellite, you want to do certain things with it. So this is the list of the certain things that we wanted to do. So first off, any satellite needs power. This is a small satellite, so power actually comes at a premium. The 4 solar panels we had could generate at most 28 watts of power, and the communication system we had, the payload, the radio, that consumed 40 watts. So as you can imagine, if I just ran that for some time, I would just run out of battery, and even with complete solar power, I would not be able to even power that thing up. So we had to be very economical about this whole thing. We would have to be pointing at the sun as much as we can so that we can store up enough power to use sunlight plus onboard battery power to run the experiment. Because when you're in orbit, this kind of an orbit, you have 90 minutes. You're orbiting Earth every 90 minutes. And out of the 90 minutes, you have about 40 minutes of sun. No, sorry, 45 minutes of sunlight and 45 minutes of darkness. So while you're on the dark, you're rotating, right? So 90 minutes period, yeah. So when you're on the dark side, you have to keep your batteries alive because it gets very cold very fast. So you have to basically have a heater running just to keep your batteries alive throughout the dark side. And then you come out of the dark side and you get some power. So you want to maximize how much power you're generating. And for that, take your solar panels, point it at the sun. That's the way to do it. And when you launch a satellite, it is doing random things. It's like if I took this and just threw it. It's tumbling in weird directions. We don't know how it's pointed. So every satellite that goes out, unless it's placed in a certain orbit carefully, which happens with the big mission satellites, you have to do some kind of initial sun pointing. And while you're doing that, you're probably not generating a lot of energy. So we had to make sure that when we do that, we are not going energy negative, like we're not depleting our battery already. Then once we do all of this, we are sun pointed, we still have to make sure that we are pointed that way stably, because if there is pointing jitter, by jitter I mean if we are doing this, then as we transmit data, we're basically going to lose track of where the ground station is. Because even though we have a phased array that's steering the beam and so on, it can only do that at a certain rate. And then let's say we get hit by a micrometeorite or a gravitational gradient. Any disturbance to the pointing that we have, we must be able to recover fast, because otherwise, again, the same problem. We're not sun pointed, we'll lose power just sort of sustaining ourselves, and if we go into energy negative, the mission is over. And on top of all of this is just staying alive. On top of this, we wanted to do this very ambitious thing where we wouldn't know where our ground station is. We are orbiting the Earth blindly, and we're just listening for a beacon from the ground. And once we hear that beacon, we would like to basically tighten our beam so that we could transmit more data, and then track that beacon signal while that's happening. So that's the last two things. Search for the beacon signal, and then lock onto it and transmit your data. So this is a very simple demonstration that we're trying to do. We're trying to do a simple communication satellite, but even that has so much simple operational complexity. That's something to keep in mind. So that, and these are the requirements that we set for the attitude control system, that we would have to support 6 months of nominal lifetime. We would set the satellite up so that it's spinning at about 10 revolutions a minute, about the z-axis, which is like the long axis of the spacecraft. Now, why is that? Because if you're basically a spinning top, then you have angular momentum, and that would resist any sort of external forces that would try to change its orientation. And since we're rotating like this, you can have a nutation around the central spin axis. We wanted to minimize that to less than 5 degrees, because otherwise you'll have to move again your beam too much, just because of the nutation. And same goes for the sun pointing accuracy, because if you're off more than 5 degrees, then cosine of that it kind of starts to drop down pretty fast, just to increase the power envelope. And on top of that, we wanted to be able to charge from Earth's albedo, because when the satellite if this is Earth and the satellite is spinning, and this is where sun is, it will rotate like this. It won't go like this. That's a gravity gradient stabilized thing, which ours was not. So we wanted to basically, when we're like down here, you're still getting some reflected light. Or if somehow I'm pointed the other way. Sun is that way, Earth is here. Earth is reflecting about 30% of sunlight. So we wanted to get some charge out of it if possible. And what is this against? We are at 400 kilometers. We have opened up basically 4 sails, because we have 4 solar panels that go up from the sides like this. So we have increased our surface area considerably. That increases drag by a lot. Drag goes with area. So that basically meant that we have a lot of disturbance because our thing is sort of heavy on one end. We have this sail on top, and we have a limited power budget. So the attitude, determination, and control system had to deal with all of these different things.
You mentioned about the beacon in the
Yeah.
previous slide.
Yeah.
But these satellites, if they want, they can have some GPS.
Yes,
detection.
exactly. Now, why did we not do that? I'll come to that in a minute. So now, what are the issues with what I have discussed so far? So the issues are, it's too ambitious. Why is it too ambitious? We had too little time. We had 3 years to deliver on this project with undergraduate students. We had too little money. I believe the funding was $500,000, and out of that, 250 was for launch services and 250 for everything else. That included time of the students, time of the PIs, all the components, everything. And since this was done with undergrad students, they had too little experience. And since we wanted to do this with mostly undergrads, there was not enough supervision or leadership. So that's the first set of problems. Then second set of problems, decisions that look good on paper, but they're horrible in practice. For example, so I mentioned that we had solar panels that opened up like this. So before they opened up, they had to be basically packed tight, sent up to space, and then deployed. The way we decided to do that was we had basically a nylon rope going through these little holes over here. So imagine you have like my hands like this. I close my hands, and then I tie a rope across like this. So my hands are now this, and if I cut that rope, I can do that. So that's the method we chose to do this. What's the problem? Now I can basically use this entire middle section at the middle of my spacecraft. That's empty. And I have basically just 2 ropes going through it. I have to cut those ropes, and I have to make sure I cut those ropes, because otherwise the whole mission is dead. And the solar cells won't open. I won't get any power. The antennas won't open. I won't get any data. So that's a single point of failure that is totally dependent on us tying a piece of nylon rope right. A huge problem. Shouldn't do that. And since we have a huge empty section in the middle, we now have a mass balancing problem. And then not using certain components due to lack of testing. So that's where what Dr. Chatterjee asks matter. That why did we do it with a beacon and not with GPS? It's because we didn't have the infrastructure to test a GPS beacon system. We also didn't have the infrastructure to actually test a gyroscopic system to determine our spin rate. So we were using only our magnetometer to not only determine when we are going to apply torque to rotate our spacecraft, we were also reliant on that to measure our spin rate. And now imagine if you have a magnetic field sensor that measures magnetic field in 3 axes, and somehow, and you're in ambient magnetic field. And somehow this magnetic field is aligned with your z-axis, and you're rotating around your z-axis. So can you even determine your rotation anymore? No. So these are all the different problems that arose because of decisions that we took that were great on paper. Don't use something you can't test. Great. But that also means I can't do a bunch of things. It's basically kneecapping ourselves. And on top of that, since we had little time, little money, little experience, we had to do many last-minute changes to accommodate the different goals. And there was a huge lack of testing because at the end of the day, it was a small team. Because what happens with undergrad students, at least in the US, is they will probably come on board for a semester or 2 doing their undergraduate capstone project. It's a research project that they have to do in a team. But once they're sort of in the last 2 years of school. So once they're done, they're probably very few of them are sticking around. Either they're doing different research or they're going to industry and getting a job. Like, why would you be a student when you can get a job, right? So all of those I identified as core issues to Spacehawk while I was working on it. And I sunk like from 2018 to 2021, 3 years of my life in this project. And I decided never again will I do a project like this. But not everything about this experience was bad, because I learned a bunch of things. I would have never dreamt of working on a satellite sort of by myself if this project didn't happen. I learned a lot. That's great. And other opportunities did come along. I'm sorry about the quality of these pictures. I don't like to take pictures. These pictures are actually from the patent application that we did. So really sorry about the quality of them. But let me explain this picture real quickly. So this weird box thing with this cable that you see, this is actually a Cubesat launcher. So this whole box thing, this box situation going on, that's a Cubesat launcher. This little thing with the blue panels, that's actually our Cubesat. We put it in the launcher to do a pre-flight vibration testing. And when we did this, we saw something strange. You see this little bit of coil there? That's the spring. That's the spring that actually pushes the CubeSats out. And they have the classic round and square thing problem. So how do they solve it? They have a cylindrical spring. They have this little adapter thingy that's like a little can and a little cuboid sort of attached together, so that the spring goes around the cylinder, and then the cuboid pushes your other cuboids, your CubeSats, out. And this little piece, it's a block of aluminum that's launched every time a CubeSat is launched. It's taken up to space every time a CubeSat launcher is taken up to space, and it's just thrown out. It's space junk. It's debris. So when I saw this, I was like, why can't I put a satellite in that? Who's stopping me from doing that? So I asked the guys, like, hey, can I do that? And they were like, yeah, you can do that. I'll even give you a free ride if you can make one. I was like, okay, sounds great. So pretty much in the next 3 days, this is what I cooked up. This is a concept, as you can tell, but I guess it was pretty fleshed out even back then. This is 2021. So the idea is there's a cylinder. I take that, I hollow that out, and I'll cram most of the satellite bus into that, because then I don't have to worry about other people conforming to a weird shape. A cylinder is a pretty weird shape. I have a lid. I can attach antennas to the lid, for example. I can attach a sun sensor to the lid. It's going to tell me where the sun is. Then I have the cuboid section. And if I take up very, very little space in the cuboid, I can give 3U of space to anyone who wants to put an experiment in a very small CubeSat that can potentially fly for free, because they're flying this shape every time a CubeSat flies and throwing that out of the chute. It's just getting wasted. So we're like, okay, that sounds like a plan. This is a good drawing, but how far can we go from there? So now we have turned that problem that we had, that we tried to make a very ambitious satellite. And in that process, we found out that there is this opportunity that we have. Now, how can we exploit that opportunity? So we have a small cylinder that's hard to use, but people have already used that. They have used it for a little bit of extra space to have one extra lens for their telescope, or put an antenna there, but there's nothing standard there. So there's no consensus. So that's what we want to do. We want to standardize this so that anyone can use this in a certain way, and then they're free to do whatever with the rest of the satellite. So that's the first opportunity. You cram the bus function in the cylinder. For example, your attitude determination and control system, the EPS, communication, payload, all of these are electronics. And thanks to consumer electronics, we all have things in our pockets like this. This is a few thousand times, probably 1 million times more powerful than the Apollo guidance computer. And if I took this, cut it up, I would probably fit this whole thing in that cylinder with room to spare. So imagine what we can do if we want to get creative there. Then there are additional things we can do. This is a cylinder that has a fairly large cross-sectional area. And if you remember your physics, thanks, I got educated here, so I know my physics a little bit. So torque is current times area cross product with a magnetic field. So if you want to make a magnetic torquer, what better way to do that than take a piece of wire and just wrap it around your cylinder? You have a large area, you can shoot some current through it, you have Earth's magnetic field, and you can push against it. Free room to do your magnetic field stuff, shenanigans. And then we have the additional opportunity to we have the half U that we want to leave for any of you guys here to make an experiment and fly it on this thing. So if I make a standard payload interface, then you can make a payload. We can stick this in. We can chuck that plug that they use, and we now have a complete satellite that goes up for very little cost. And now, since I have crammed most of the bus functions in this, if you want to make this longer, go ahead, be my guest. You can have more than the standard 3U for your CubeSat if you want. And on top of that, if I play this whole game right, I can repurpose parts of the satellite for education, for Internet of Things, for high altitude balloon flights. And I have one of those things right here. I'm going to pass this around. This is for a classroom, but I have actually flown this on a high altitude balloon last September. So there you go. You can take a look at that. So now let's go down to the design philosophy that I have. So this is one of the boards that you can stick in the cylinder. And I'll describe what that board with a live demo at the end of the talk. So you guys can just look at it for now. So the design philosophy that I go with, or my design philosophy, is really identifying the critical problems that you need to solve in order to move forward with doing the rest of the things that you mostly understand. So my first design philosophy here is reuse as much as you can. So on Spacehawk, what we did was we either got most things off the shelf from different companies that do not talk to each other, so they have their own ways of doing things, and sometimes I found those to be problematic and honestly stupid. So my first principle is reuse as much as you can. So how do I reuse? I want to build every subsystem sort of like a body of a robot. So think of one robot that walks, one robot that jumps. So these are doing different functions, but doesn't mean that the brain that's on these robots have to be different. They're probably running different code, but the hardware does not have to be different. So that's where this comes in. This is our concept for the different boards. It's kind of different from what you have in hand, but it's an iteration of this. So the way this is made is there's this little square board that you see on this other green board, right? So this square board is sort of the brain. I can make hundreds of these. This is fairly small and cheap. And it's one thing. I make it once, I verify it once, test it once. That's done. And then I can make this baseboard for the different functions that I want. I can test that independently. So that makes my work less, right? Because if I had to copy this design down onto each and every board, then I would have to verify that to be correct each and every time. But now I don't.
There is the Raspberry Pi logo.
Yes, so this is a Raspberry Pi microcontroller. That's the microcontroller I'm using for this. Right now, I can go into more technical detail about this, but I think I'll bore most people. So we can talk about it later. Then reduce massive wires. So for that, use stackable connectors for the boards in PC104 style, but not PC104 because that stuff is huge. So these connectors that you see on the two sides, I can take another board like the one that I've given you. You can just take another one, plop it right on top of that, and they're going to work. They'll have the correct electrical connections, the correct data sharing connections between them. And that makes life very easy. You can basically build up a satellite like a little Lego. Then get as much mileage out of parts as possible. So, for example, the lid of the cylinder. I want that to double as my GPS antenna. I want that to double as my sun sensor. I want the cylindrical body that's basically housing all of these different bus functions to double as our Z torque coil. And then occupy as little area as possible in the cube section, the payload section. So, for example, in Spacehawk, we use cylindrical batteries, 18650, that's the standard. So it's 18 millimeters tall, 18 millimeters diameter, 65 millimeters tall. That's fairly thick. But if you use a battery like that's in your cell phone, those are flatter and thinner. They're not as heavy because they use a plastic cover instead of a whole metal cover. But if you can qualify them for space use, voila, you can use them and save space and mass. Then when we flew Spacehawk, we used these literal rods, like torque rods for X and Y directions. But torque rods are, they're not gigantic, but they do add thickness. So instead, just use a PCB because again, you have the sidewalls. And again, more area is more torque. So you can basically leverage that to not take up any space, give your satellite structure as well as your magnetic torque coils. For solar panel deployment, don't put a piece of wire through your satellite and take up space. Just use something on the wall that is basically a latch. You unlatch it and it opens up. That does two things. One is it saves you space, and second, it's repeatable. So for example, if you want to try this out before you actually send out this thing to space and you'll never get it back, you can actually try that, okay, my thing actually does open. My spring strength is actually good. And then on the antenna, punch a hole for science to look through. So for example, this is our first prototype of the magnetic torque coil. So you can see this is basically a flat panel with a spiral on it. And if I send a current through the spiral, then I'll have a magnetic moment because it's current and area. It's in a loop. And then this is an antenna that we've been working on. This antenna is actually pretty cool because most antennas are either it's like a dish, or if it's a flat antenna, it doesn't really have a hole in the middle. A hole in the middle really throws the antennas off. But this antenna, it's a 4-inch by 4-inch thing, and it has a hole in the middle. It's tuned for 900 megahertz-ish frequency, which is a public band, so anyone can transmit in that band under certain power regimes. So testing this in the lab is easy. You don't have to go to FCC or whoever the regulatory body in your country is to get a license to do your things. So I believe these design philosophies do a few things. One is it allows people to basically get the parts, make the satellite themselves. It tries to reduce and reuse as much of the satellite as possible. And it tries to give the payload science as much room as possible. So that was my goal for this little tiny CubeSat. But design and philosophy is only a part of it. The rest, the other most important part is tooling. So for example, in tooling, I'll keep software as part of tooling because when you're developing it, it's something that you're carrying over to other projects. It's not, once you write a piece of software, it's not for just one project. So in our case, the software, it already has some reuse built in because of the common brain hardware. Once you program for the brain sort of once, you're only changing out some certain things and not doing much else. Then, yeah, there are some philosophies about how you do that. So we have to use a strongly typed, memory-safe, garbage collection-free language because we want this thing to be predictable, reliable in space. In space, if you pause for 1 millisecond because in Python you created 20,000 objects and you are out of memory and you are reclaiming that memory, you're probably going to miss a micrometeorite hitting you, and then you'll have other problems. You don't want that. And then whatever you do, you want it to be traceable. So you want it to be testable, predictable. So it's all sort of part of that tooling. And then the other very important thing that I missed doing during Spacehawk because of lack of time and money is testing. You have to test everything. Your algorithms have to be tested. The projected performance has to be tested. You always have to have more margins than you think you need. And if you have two parts of a system, for example, if you have a radio, one part of that goes on your satellite, one part of it stays on the ground to communicate. You have to develop them simultaneously, and you have to test them in as apples to apples as configuration as possible to make sure it actually works when you put your thing to space, and you can't pull it back again if you have to change something on it. So those are sort of the lessons that I learned and I try to apply. So to that end, we got a huge funding from the state of Massachusetts, and we built these different test facilities. So on the left, we have our anechoic chamber. This is actually the Spacehawk antenna that we flew. What this will help us with is it's going to help us actually, for example, measure our antenna pattern, how much power we can put out, what data rates can we actually have in space-like environment, and so on. This is a magnetic coil setup. So if I want to test my attitude control and determination system, I can put one of those things on, for example, on an air bearing. I can simulate Earth's magnetic field as it would be in space if the thing was rotating and whatnot. And I can have it actually spin in that and validate that, okay, the algorithm that's running is correct. And then we have a bunch of materials testing. So this is a controlled humidity and temperature chamber. So we can subject materials to different humidity and temperature conditions to see how they behave. And then this is an outgassing chamber. So we can put a material in there, heat it up, pull vacuum on it, or make it cold, pull vacuum on it, and see how it loses mass, for example. For example, if I have a piece of plastic in my CubeSat and I have some optical components next to it, if my plastic is basically going to vent and coat all my optics so that it's going to be rendered useless, I can do all of that testing before I fly my thing. That's also very important. The cones. So these cones basically trap RF energy, so that makes it anti-reflective. So if you go in that room and blast out RF between 0 and 40 gigahertz, nothing will come back. Nothing will reflect back. It's as if being in an infinitely open space. So, for example, in that room, if you go and stand and talk, you won't hear any reflections back. There's no echo. Yes, so those are sound anechoic chambers.
Space.
Right. So this is a radio anechoic chamber, but sort of similar ideas. And then, as I said, tooling we can reuse. So this.
You just said that in vacuum plastic tend to.
Yes, outgas. Yes. It will not really evaporate, but it will outgas. It'll degas, yes.
And that can.
Right.
Gas, what do you need?
So let's say I have like some kind of a plastic, right? Like ethylene plastic. So it may give off some of the volatiles, and that's going to go and land on something, and it may chemically react and coat something. And then you'll lose your optical efficiency, or you'll lose your surface property, and it'll basically render your optics suboptimal. If not, we can change temperatures, yes, because in space, like one side, like the hot side can get very hot and the cold side can get very cold because you're just in sunlight and you're insulated, right? So it's mostly radiation, and that's not the most efficient thing. So we can also, again, reuse existing tooling. So this is an environmental simulator that I built for Spacehawk. So this simulates this creates the Earth environment for the attitude control system. So it creates the correct magnetic field, the correct sunlight. But what I had to do back then is I had to basically jerry-rig a bunch of these different things to do the environmental testing. So these are the different sun simulators. So we have the sun sensors under these boxes, and we have LEDs. So the LEDs are changing brightness depending on where the sun is. And the sensors are supposed to read that sunlight value and basically give me a 3D position of where the sun is. Then we have this very jerry-rigged sort of Helmholtz coil that's generating the correct magnetic field with this very handmade driver. So that now has been replaced with this system, right? So it's bigger. We can do actually stick a 12U CubeSat in there if we want to and do the test better. But we can, again, reuse the existing software. No, actually nothing spins on this. But the idea is on this central platform, you can put something called an air bearing. So it's like an air hockey table. So it has very, very low friction. So once you put something on that, now imagine a spherical table and you put a sphere on it. So then the sphere is free to basically rotate in all directions, right? So that's what you can do in a setup like this. This setup is not complete. I haven't got time to work on it yet, but at some point I'll get to it. So yeah, so these are basically the things that I did from Spacehawk, and now they have evolved to other things. So these are our old simulation results. This is all in software, so that's why this looks so nice. But when we do this in actual hardware, we'll have all the noises in. So that's the other challenge. You can have a great tool that works well on paper, but often in practice they don't. So that's why testing is very important. So now I'm going to stop the blabbering about part, and it's time for an actual demo. But it'll probably take a second to set up. So let's see if we can do that. And I'll probably have to end the Zoom here because I'll lose Wi-Fi on my laptop. It's a part of the demo.
Okay, do what you want to do.
Okay. So this is the end of the talk in that regard. So let's have the questions now, and then we'll go through the demo and have more questions. How about that?
Questions?
So, but can I go to a title? I mean,
Of course.
I'm so careful in hearing this.
There we go.
So, have you flown your CubeSat?
That one I have. Yes.
I thought that for a video of that.
Oh, I will show you guys pictures later. Yes. I mean, I don't have a video of the actual launch, but I have pictures from the ISS. Yes.
Space.
Yes.
Yeah.
Right. So the performance is abysmal failure because lack of testing, and we were unlucky enough that a CME hit pretty much immediately after we launched. So that was also the launch where like a bunch of Starlink satellites were lost. We were also part of that. So we were basically afloat for 15 days before.
So next is the one that you.
Yes.
What was the goal?
So the goal of that was the high-speed communication thing. So yeah, you have, no. We didn't have time to do that, one. So we tested what we could, but we couldn't stress test the system as much as we wanted to. So in this world, the common wisdom is 100 hours or a week of continuous testing as it would operate. And if you can't do that, there is really not enough confidence in what you fly. So we totally did not get to do that.
But you didn't talk about the other like camera and stuff that
No.
was actually flown and got
No.
data.
No,
Why
this
is it?
talk is not about that. This talk is about failures. I think it's very important to know that.
I mean, there should be some success at the end of failure.
Well, I guess the fact that everyone has at this point probably touched something that has flown on a balloon and done something is
No,
a
but
success.
Okay, I guess
Yeah.
you can deserve judgment.
Yeah.
Yes.
Questions?
Questions? Please.
You briefly said about that the satellites facing the sun and the other side facing. But these are very small satellites. Right?
Yeah.
The thermal stress. I'm guessing you're talking about the thermal stress kind of thing. Will that
It's
be a-
two things. One is thermal stress, and the most important thing for me is power, right? Because if I point it the other way, I'm literally losing 70% of power, right? And as for thermal stress, if you model these things, the face that's facing the sun is at 130 Celsius, and the other side is at -70. That's the thermal. We're talking about a thermal gradient of 200 Celsius across like of this much. Question?
Yes. So you talked about getting power from the albedo.
Yes.
How much do you expect?
So albedo is 30%, but it has a different spectral characteristics.
Okay.
So all of that combined, you can get about 20% of sunlight. 20% of sunlight. Yeah.
But I did not understand that part where you said that you require 40 watts of power.
Yeah. 28, yes. Yeah.
Power from well.
No, all the extra power I'm getting is because I have a battery. I can store another 30 watt hour of energy in the battery. So when I'm in sunlight, I have 30 watts coming in, and I have a 30 watt hour reserve. So combining that, I have enough power to run the experiment for 10 minutes. Yes. Yeah. Yeah. Right. So out of the 90 minutes, most of the times we would not do anything because it's a communication payload, right? So it has to basically see our ground station antenna. So it has to be the right kind of satellite pass. And those passes usually happen about 4 to 5 times every 2 months. Because once it goes overhead, then there is a phase mismatch because the orbital plane is shifting, and it has to shift back, and that takes about a month and a half to happen. So we're talking about actually having to run the payload for about 5 minutes every orbit, 5 orbits every 2-ish months.
The angular scale.
Huh?
What angular
So angular scale of the beam. So the beam is 20 degrees wide. Right, right.
Station antenna can
The station antenna can point in any direction. Right. But even then, what you're covering here, like the station antenna has to cover the whole 180 degrees basically in a pass, right? But the satellite is moving, and that gives you about 7-ish minutes of contact time out of
45 minutes.
out of the orbit. Yes, about 7 minutes on a good day, 2 minutes on a bad day of contact time.
And how do you improve that?
You can't. It's orbital. It's the orbit. You can't change the orbit. So the maximum contact time that you get from an orbit like this is about 7 minutes. And that's why the data rate is important. If you have only one station, then you need to dump all of your data as fast as you can. Yeah. Right. You have to store the data on board for the rest of the time. Either that, or you have to have a global network of, yes, a global network of stations, which does exist.
Uncontrollable spin.
Yes. So right. So you have to have an algorithm that actually measures your spin and then fires, like pushes against the Earth's magnetic field, so that you slowly orient yourself. Like the point here is all of these mechanisms that are mostly on CubeSats are slow. That's the other sort of big problem. The way to gain fast control is through reaction wheels or thrusters. Reaction wheels are unlimited, but they're spinning, right? So they have after you basically gain certain amount of angular momentum, you have to be able to dissipate that, because then you can spin any faster without breaking the thing. So that's where you still have to use magnetic torquers to basically dissipate all of that. And thrusters are basically few use wonders, right? You can use them for a limited period of time. You run out of fuel, you're done. So that's why on a CubeSat, magnetic torquers are great, because it's low power. It's basically unlimited use, but the downside is it's slow. And that really all comes down to a space volume power trade-off, right? If you have enough room to put reaction wheels or thrusters, you can do that. If you don't have that, then magnetic forkers are the way to go. So on the small version that's going to go in the plug, we don't have enough room to do anything but use magnetic foils. So that's the goal there. But if you want to make a bigger satellite where you specifically want either very fast pointing or like very accurate pointing or very fast slew, you will have to use reaction wheels, and you have to basically budget for that in your satellite.
Other questions? So your abstract had something called the chickadee
Yes.
family of satellites.
So the
Can you
chickadee
talk-
family of satellites is this new thing that I talked about that's going to occupy the space in the plug. And it's the chickadee family because the chickadee is the actual satellite that's going to go in the plug form factor. But since chickadee is built up of different parts that you basically can stick together like Legos, you can have something like this. This we have